Introduction to the Delta-Y Transformer Connection, Part 1. This is the first part of the series for the Introduction to the Delta-Y Transformer Connection. In this series, we're going to focus heavily on the Delta connection for obvious reasons. I found the Delta connection to be much more complex, confusing, and easy to mess up compared to the Y connection. In this module, we're going to simply draw and observe the Delta-Y Transformer connection. In Part 2, we'll look at voltage quantity. Let's begin by drawing a single-phase transformer with two windings. We'll assume that the winding on the left is the primary side, or the high voltage side, or the source side, and the winding on the right is the secondary side, or the low voltage side, or the load side. We'll draw our polarity marks to indicate the polarity side of the winding, and we'll also indicate magnetic coupling with two parallel lines. And lastly, we'll assume that the primary line-to-line voltage is 4160 volts and the secondary line-to-line voltage is 480 volts. What we have so far is a single-phase transformer, and we'll assign a capital A to the primary winding and lowercase a to the secondary winding. To make a three-phase transformer, we'll simply add winding B and winding C. Since we're illustrating a Delta-Y transformer connection, let's start by connecting our secondary windings in Y. We're going to connect winding A, winding B, and winding C together. And for the sake of simplicity, we're going to ground the neutral wire. This is a Y-grounded transformer connection. The Y-grounded transformer connection has different characteristics than the Y-ungrounded transformer connection. This will be discussed in a different module. Now we'll connect our primary windings in Delta. There are many ways to connect a transformer in Delta, and each connection gives us a unique characteristic. We'll explore different Delta transformer connection in later modules. But one of the most common Delta connection is called a Delta AB or DY1 connection, and we'll draw this Delta connection like such. And this, my friends, is a Delta-Y grounded three-phase transformer connection. Introduction to the Delta-Y transformer connection, Part 2. In Part 1, we illustrated a very commonly connected Delta-Y transformer. In Part 2, we'll look at the relationship between the line-to-line voltage and phase voltage for the Delta and Y connections. We understand that phase voltages are voltages measured across transformer windings. Let's illustrate primary phase A voltage, which is measured across the polarity side of winding A and the non-polarity side of winding A. Similarly, we'll illustrate primary phase B voltage and primary phase C voltage. And on the secondary side, we'll illustrate secondary phase A voltage, secondary phase B voltage, and secondary phase C voltage. Line-to-line voltages, however, are measured across two lines. The most common line-to-line voltages are measured across line A and line B, from line B to line C, and from line C to line A. So on the primary side where our transformer is connected in Delta, we should expect the line-to-line voltage across line A and line B to equal phase A voltage. Now it's very important to visually verify this relationship to get an intuitive understanding. Suppose we label point A and point B as the point of measurements. Point A is the same point on the line as the polarity side of winding A. And point B is the same point on the line as the non-polarity side of winding A. So if we measured across point A and point B, we're actually measuring across the polarity side of winding A and the non-polarity side of winding A, which we earlier defined as our phase A voltage. Similarly, the line-to-line voltage across line B and line C is equal to phase B voltage, and the line-to-line voltage across line C and line A is equal to phase C voltage. So for a delta connected transformer, we should expect the voltage across two lines to equal the voltage across a single winding. Or in other words, the line-to-line voltage equals the phase voltage. On the secondary side, where our transformer is connected in Y, we'll have a different relationship between the line-to-line voltage and phase voltage. The most common line-to-line measurements are across line A and line B, across line B and line C, and lastly across line C and line A. The line-to-line voltage measurements across line A and line B is equal to phase A voltage minus phase B voltage. For a Y-connected transformer, if we look at the magnitudes alone, we should expect that the line-to-line voltage to equal the square root of 3 times the phase voltage. There is certainly going to be some phase shift involved between the two voltages. So if you look at the phase angle relationship, we should expect a 30 degrees phase shift between the line-to-line voltage and phase voltage. Again, this is covered in great detail in a different module. So what's the line-to-line voltage between line B and line C? That's right, it's phase B voltage minus phase C voltage, which is equal to the square root of 3 times the magnitude of phase B voltage, which is also equal to the square root of 3 times the magnitude of phase C voltage, or simply the square root of 3 times the magnitude of any phase voltage. And of course, we're assuming that we have a balanced set of voltages. When I was first learning this, it helped me to visualize this relationship between the line-to-line voltage and phase voltage when looking at actual numbers. If we took a super duper voltmeter and measured across line A and line B on the primary side of our transformer, we should expect 4160 volts. This is our line-to-line voltage that we assumed in part 1. Now, since the primary side of the transformer is connected in delta, we should expect that the line-to-line voltage to equal our phase voltage. So we take our super duper voltmeter and somehow get inside our transformer and measure the difference in potential between the polarity side of winding A and the non-polarity side of winding A. We should expect a voltage of 4160 volts. Similarly, the line-to-line voltage across line B and line C should equal 4160 volts. And the line-to-line voltage across line C and line A should also equal 4160 volts. Both phase B and phase C voltages should also equal 4160 volts. So for a delta connected transformer, the line-to-line voltage is equal to the phase voltage. On the secondary side, where our transformer is connected in Y, if we measure across line A and line B, we should expect 480 volts for the line-to-line voltage. Again, this is the voltage that we defined in part 1. So what voltage should we expect if we measured across the polarity side of winding A and the non-polarity side of winding A? Well, we would have to derive that from the line-to-line voltage. Remember the relationship? For a Y-connected transformer, the line-to-line voltage across line A and line B is equal to phase A voltage minus phase B voltage, which is equal to the square root of 3 times any phase voltage. Since we already know that our line-to-line voltage is 480 volts, we simply solve for the phase voltage by dividing 480 volts by the square root of 3, which gives us approximately 277 volts. So phase A voltage is equal to 277 volts. Similarly, phase B voltage is equal to 277 volts, and phase C voltage is also equal to 277 volts. And the line-to-line voltage across line B and line C is equal to 480 volts, and the line-to-line voltage across line C and line A is equal to 480 volts. In this part, we looked at the line-to-line voltage and phase voltage relationship for a delta Y transformer connection. In part 3, we'll look at the line-to-line current and phase current relationship. Introduction to the delta-Y transformer connection, part 3. In part 2 of the series, we illustrated the relationship between line-to-line voltage and phase voltage. In part 3, we'll cover the relationship between line current and phase current for the delta-Y transformer connection. Pick up where we left off, on the secondary side of the transformer, where our transformer is connected in Y with the neutral grounded. We understand that line current, or line-to-line current as I like to call it, is a current that flows through the lines or conductors. Since we've assumed that the secondary side is our load side, we understand that the line currents will flow through our lines to our load. So line-to-line current A will flow through line A, line-to-line current B will flow through line B, and line-to-line current C will flow through line C, and they will all feed our load. We have decided to call our line currents line-to-line currents. Now, it may sound misleading, but it helps my brain to point out clearly that we're talking about the actual line current for a particular line. So if labeling this current as line currents or some other name helps you, by all means do so. As long as we clearly define our variables, we should be alright. Okay, so our transformer is connected in delta on the primary side or the source side. So this is where our source current will come from. The line-to-line current A will flow through line A. Similarly, line-to-line current B will flow through line B, and line-to-line current C will flow through line C, respectively. Remember, this line-to-line current comes from the source, like a generator, a utility, or the grid. Let's now talk about phase currents. We understand that phase currents flow through transformer windings. Let's start on the secondary side where our transformer is connected in Y. We should expect phase A current to come from winding A and flow to our load. Similarly, phase B current comes from winding B and flows to our load, and phase C current comes from winding C and flows to our load. For a Y-connected transformer, we should expect phase A current and line-to-line current A to be the same. Check out the resources section for additional information. Since phase currents flow through transformer windings, the delta transformer connection is no exception. Let's begin with winding A. Since we know that secondary phase A current flows out of the dot on the secondary side, that simply means that the primary phase A current must flow into the dot on the primary side. So primary phase A current will flow into the dot, and secondary phase A current will flow out of the dot. This makes sense, right? We're simply following the dot convention. If current goes into the dot from one side, then current must flow out of the dot on the other side. Similarly, phase B current must flow into the dot on the primary side to make secondary phase B current flow out of the dot on the secondary side. And lastly, phase C current must flow into the dot on the primary side to make secondary phase C current flow out of the dot on the secondary side. And that, my friend, is how we describe phase currents and line currents for the delta-Y transformer connection. For me personally, I found it very difficult to intuitively understand the relationship between line current and phase current for the delta-connected transformer. However, this difficulty can be easily overcome with a simple yet intuitive explanation. In part 4, we'll cover this relationship. This video was brought to you. Introduction to the delta-Y transformer connection, part 4. In part 3 of the series, we introduce line currents and phase currents for the delta-Y transformer connection. In part 4, we'll explore the relationship between line current and phase current for the delta-Y connected transformer. We understand from part 3 that primary phase A, B, and C currents flow through the polarity side of the primary windings. And the secondary phase A, B, and C currents flow out of the polarity side of the secondary windings. For a Y-connected transformer, it's very easy to see that phase currents and line currents are both equal. Check out the resources section for more information. However, for the delta-connected transformer, we don't have the same one-to-one relationship between line currents and phase currents. To understand this relationship, let's label a few things to be very clear and very concise. We will call node A1 the node that connects the polarity side of winding A and the non-polarity side of winding C. We'll call node B1 the node that connects the polarity side of winding B and the non-polarity side of winding A. And lastly, we'll call node C1 the node that connects the polarity side of winding C and the non-polarity side of winding B. We know that from part 3 that primary phase A currents flow into the polarity side of winding A and out of the non-polarity side of winding A, which means that the current that flows out of node A1 by definition is phase A current. And since the non-polarity side of winding A is connected to the polarity side of winding B, the current that goes into node B1 is the same phase A current. This makes visual sense, right? Since we define primary phase A current as the current that flows into the polarity side of winding A and out of the non-polarity side of winding A, the current that comes out of node A1 and the current that goes into node B1 is the same primary phase A current. Let's now move to phase B current. We know from part 3 that primary phase B current must flow into the polarity side of winding B and out of the non-polarity side of winding B, which means that the current that flows out of node B1 by definition is phase B current. And since the non-polarity side of winding B is connected to the polarity side of winding C, the current that goes into node C1 is the same phase B current. And lastly, let's move on to phase C current. We know from part 3 that phase C current must flow into the polarity side of winding C and out of the non-polarity side of winding C, which means that the current that comes out of node C1 by definition is phase C current. And since the non-polarity side of winding C is connected to the polarity side of winding A, the current that goes into node A1 is the same phase C current. Okay, so now that we've illustrated phase currents, let's quickly label our line currents. From part 3, we know that line-to-line current A will flow through line A into the bushing of winding A and finally into node A1. Similarly, line-to-line current B will flow through line B into the bushing of winding B and into node B1. And lastly, line-to-line current C will flow through line C into the bushing of winding C and finally into node C1. Okay, so we know exactly what's going into each node and exactly what's coming out of each node. We are now going to use Kirchhoff's current law on each node to describe the relationship between line currents and phase currents. Let's start from node A1. We can visually verify that line current A flows into node A1. Phase current C also flows into node A1. However, phase current A flows out of node A1. So when we apply KCL, or Kirchhoff's current law, we can simply express this relationship as line current A plus phase current C equals phase current A. Or in other words, line current A and phase current C goes into node A1, which is why it's on the left side of the equal sign. However, since phase current A flows out of node A1, it's on the right side of the equal sign. Simple, right? The currents that are flowing into node A1 is equal to the currents that are flowing out of node A1. Or simply, line current A plus phase current C is equal to phase current A. Similarly, for node B1, line current B plus phase current A is equal to phase current B. Line current B and phase current A are flowing into node B1, but phase current B is flowing out of node B1. And for node C1, line current C plus phase current B is equal to phase current C. Line current C and phase current B are flowing into node C1, but phase current C is flowing out of node C1. And that, my friends, is how we describe the relationship between line currents and phase currents for the delta transformer connection. We'll continue this relationship and perform phasor analysis in part 5. Introduction to the delta Y transformer connection, part 5. In part 5, we're going to perform phasor analysis on the delta Y transformer connection and look at how the square root of 3 and the 30 degrees phase shift comes into play. Okay, so this is what we illustrated in part 4. We did a nodal analysis on node A1, node B1, and node C1 and looked at the relationship between line currents and phase currents. And these are the equations that we came up with. In these equations, we said that the line current A plus the phase current C equals phase current A, right? Now we're going to evaluate this particular equation and look from a phasor diagram's perspective. Okay, let's rewrite these equations into something that makes a little more sense. Okay, so all we're going to do is take this phase current and move it on the other side of the equation. Okay, so let me zoom in here. Okay, so we're going to rewrite this equation and solve for the line current A. So line current A equals phase current A minus phase current C. Similarly, line current B equals phase current B minus phase current A. And line current C equals phase current C minus phase current B. Okay, so now that we've written our equations like this, let's define our phase values. So our phase values are the currents that are flowing through our winding. So we're going to define what our phase A current is going to look like. We're going to define phase B current and phase C currents. So we're going to define these currents and create a balanced system. So let's say that phase current A on the primary side equals 1000 amps at 0 degrees. And phase current B equals 1000 amps at 240 degrees. And lastly, phase current C equals 1000 amps at 120 degrees. Okay, so now we're going to draw these phasors, alright? Remember, these phasors are just the currents that are flowing through the primary windings. Keep in mind the big picture of what we're trying to solve. We're performing the phasor analysis because we want to relate this line current here with actually this phase current and this phase current. So we're doing a nodal analysis on node A1, and what we're actually trying to solve with our phasor diagram is this particular equation. Alright, we're going to try to find out what this line current equals when we subtract our phase current A minus phase current C. Let's draw a phasor diagram. Alright, so this is what our phasor diagram looks like. This line right here at the 0 degrees mark, this is our reference line, okay? And this phasor that's going through our reference line, which is at 0 degrees, this is phase A current. And what we're saying is that from this origin point here to this point here is 1000 amps. and the angle is at 0 degrees, which is the same direction as our reference line. This phasor here, this is our phase B current. And from this origin here to this mark here is 1000 amps. And the angle, which is 240 degrees, is what we defined, that angle is from this reference line going in a counterclockwise direction until we've gone 240 degrees. So this angle is 240 degrees. So we are defining this phase B current here at the angle of 240 degrees, okay? And lastly, this phasor here is our phase C current. Again, it's from the origin to the end of the tip here is 1000 amps. In the angle from the reference line going counterclockwise 120 degrees to get to this phasor. So phase C current, which is this current here, equals 1000 amps at 120 degrees. All right. So let's mark these angles here. So we're saying that this angle right here is 120 degrees, and we're saying that this angle here is 240 degrees. Okay. And now let's clean this up a little bit. Okay, so we're going to take these phasors and subtract phase A current with phase C current, and then look at what our line current A looks like. Okay, so we're going to take these phasors and subtract phase A current with phase C current, and then look at what our line current A looks like. Alright, so here's phase A current, and here is phase C current. Now, if we were to perform phase A current plus phase C current, we would do this through what we call a head-to-tail method. And how that works is very simple. We pick up phase C current and add it to the head of phase A current. And the resultant vector starts from the origin and goes towards the head of phase C current. So this right here is our resultant vector. And this resultant vector equals phase A current plus phase C current. However, this is not what we want. What we want to equate is this equation, phase A current minus phase C current. So let's clean this up a little bit and put phase C current back to where it was. Okay, now because there's a minus sign that's associated with phase C current, we have to pick up phase C current and rotate it 180 degrees. So phase C current becomes like this. So this phasor here is negative phase C current. And now let's pick this up again and connect it to the head of phase A current. So now we're going to connect it like that, okay? Now the resultant vector starts from the origin and ends at the head of negative phase C current. Now notice that the resultant vector is a lot longer now, right? And the resultant vector represents phase A current minus phase C current. Now believe it or not, this phasor diagram actually represents this particular equation, right? And this resultant vector is actually representing this line current here. So what we're saying when comparing line current with phase current A, now remember this is phase current A here and this is line current A here. So let's label that a little better. We see that the line current is a lot larger than our phase current, right? So this is our phase current here and this is our line current. So the magnitude of our line current, which starts from the origin and ends at this tip here, that is a lot larger than our phase current. In fact, if we compare the two, we will find that the line current is actually the square root of 3 times larger than our phase current. So if we take our phase current here and line it up with our line current, we'll be at this point here. But then we would have to stretch it, or we would have to multiply it by the square root of 3, or 1.73, to make it equal our line current. So that's the first observation, that our line current is a square root of 3 times larger than our phase current, okay? Now, also notice that our line current has a phase shift that's associated with it, right? So if all the phasors were rotating in a counterclockwise direction, which they should according to international standards, they were all rotating in a counterclockwise direction, we will see that the line current has a 30 degrees phase shift, okay? So this 30 degrees, so number 2 line current has a 30 degrees phase shift with respect to phase current. Before we conclude here, when I was first learning this particular phasor analysis was very complicated. It didn't sit with me very well. So let's take a step back and walk through this step by step, okay? So what we're actually doing with this phasor analysis is we're trying to compute this particular equation. And what we're saying is if we subtract phase current A minus phase current C, we'll get line current A. And this is exactly what we did. We took phase current A and we subtracted phase current C, and what we got right here is line current A, okay? And all we're saying is if we compare phase current A, which is this phasor here, with this line current A, which is this phasor here, we'll see that the line current is a lot larger than our phase current, okay? Not only is it larger, but it also has a 30 degrees phase shift. This line current has a 30 degrees phase shift. So going back to our diagram, what we're saying is that this line current here, if we compare this line current with this phase current, which is the phase current that's flowing through the primary phase A winding, this line current is going to be square root of 3 times larger than this phase current. And this line current is also going to have a 30 degrees phase shift with this phase A current, okay? So let's take another step back and ask ourselves, why is our line currents different from our phase current? Is because when we set our phase A, B, and C currents, we said that we would have a balanced system. And in this balanced system, we have 120 degrees phase shift between our three phasors, all right? So phase A is 120 degrees apart from phase B, and phase B is 120 degrees apart from phase C. Now, because we have a balanced system, and because the phase currents are 120 degrees apart, when we're subtracting one phase current with another phase current, the angles is the magic that gets you the square root of 3 times larger and the 30 degrees phase shift. So it's the angle of phase A current, which is at 0 degrees, right, which we define here, and the angle of phase C current, which is at 120 degrees, which we define here. That's what's causing the square root of 3 times difference and a 30 degrees phase shift between the phase current and the line current. Introduction to the delta Y transformer connection, Part 5C. In this part, we'll continue to do our phasor analysis and look at what the relationship is between line currents and phase currents. In the last part, we looked at the phasor analysis between line current A and phase current A and phase current C, and saw that the line current A compared to the phase current A, there's a magnitude difference of the square root of 3, and there's a phase difference of 30 degrees between these two currents. So in this video, let's look at the relationship between line current B and phase current B and see if we get the same relationship. Okay, so what we're going to analyze is this particular equation. So we know that line current B, which is this current here, is equal to phase current B, which is going into the winding B, the phase current B, minus phase current A, which is coming from winding A. Now, the reason why the equation is set up like this is because our delta connection is set up in this particular fashion, where the polarity side of winding B is connected to node B1 and the non-polarity side of winding A is also connected to node B1. Let's evaluate this equation. Alright, so we have a balanced system like we did in the previous example. This is what we did in the previous example. So I'm going to put phase C back to where it was. Okay, so here's phase A. It's at the 0 degrees mark and it's defined by this particular equation. Here is phase B. It's at the 240 degree mark and it's defined by this equation. And here is phase C, which is at the 120 degrees mark, which is defined by this equation. Now this is what we call a balanced system, and there's a dedicated video that talks about this particular setup. Okay, so we're going to evaluate this equation here. line current B is equal to phase current B minus phase current A. So what we're going to do is we're going to pick up phase current A and add it to the head of phase current B. Now the resultant vector would equal phase current B plus phase current A, but that's not what we want. We want phase current B minus phase current A. So what we would have to take phase current A, pick that up and rotate it 180 degrees, and that would equal negative phase current A. So our resultant vector, which starts from the origin and ends at the tip of negative phase A current, that resultant vector equals phase current B minus phase current A. And that essentially equals line current B, right? So our line current B, let's remove this. The magnitude of line current B is the square root of 3 times phase current B. Very similar to our last example in part 5b, right? And our line current B is also 30 degrees lagging compared to phase current B. Now it's lagging because all of the phasors, we assume that they're all rotating in a counterclockwise direction. Phase current B is ahead of line current B, right? As they rotate in the counterclockwise direction. So line current B lags phase current B by 30 degrees. So 30 degrees is actually the angle difference between those two phasors, right? So very similar to part 5b. Okay, let's evaluate this equation very quickly. Our line current C, which is this current here, right, is equal to phase current C, which is the current that's going to phase C winding, minus phase current B, which is the current that's coming from winding B and into node C1. You see that? All right, so we're going to evaluate this particular equation now. So what we'll do is we'll leave this line current B as it is, but we'll make a copy of phase current B and we'll put it here at the head of phase current C, but we have to rotate it 180 degrees because it's negative phase current B. So this right here, we're going to label this negative phase current B. The resultant vector is going to start at the origin and end at this tip here. Now our resultant vector equals phase current C minus phase current B, right? So comparing it to phase current C, our resultant vector, which is our line current C, our resultant vector is the square root of 3 times larger than phase current C, and it also has a 30 degrees phase shift compared to phase current C. All right, you see that? So there's, as they all rotate in the counterclockwise direction, there's a 30 degrees phase shift between phase C current and line current C. Okay, so what we're saying essentially is that line current C, which is going into node C1, if we compare line current C with phase current C, which is going to winding C of our transformer, of our delta connected transformer, we will see that the line current is square root of 3 times larger than this particular phase current, and our line current is also has a 30 degrees phase shift for this delta connection compared to this particular phase C current. Right? Okay, so returning back to our phasor diagram, now in this diagram I quickly redrew our line current A like we did in part 5b. So in this complete phasor diagram, we see that phase A current is here, phase B current here, phase C current is here, and in the blue we have line current, which is, this is line current A, this is line current C, and this is line current B. We see that the line currents have the same magnitude. The line current also have 120 degrees difference between each of them. So we have 120 degrees different phase difference here, 120 degrees here, and 120 degrees phase difference here. Okay, and they're both all three of them have the same magnitude, which is the square root of 3 times the phase current. In this example, we can see that the line currents are a balanced set of three-phase currents. Okay, and we see very, very clearly that the line currents lag the phase current by 30 degrees. All of the line currents lag the phase current by 30 degrees. Now, to get the update in when part 6 is going to come out, Introduction to the Delta Y Transformer Connection, Part 6a. In this part, we'll talk about the voltage phasor diagram for the Delta Transformer connection. So basically, we're going to understand how this particular transformer diagram that's often found in like nameplates, for example, we'll find out exactly how this is drawn and what this represents. If you haven't already, go ahead and click on the button on the bottom right side of your screen and click on subscribe. You want to subscribe and get notified exactly when the next part of this video is going to come out. Okay, so let's scroll down and then look at what we've done in the past. So in part 2 of this video, which you'll find a link right here, in part 2 we talked about the line-to-line voltage versus phase voltage relationship for both the delta connection as well as the Y or star connection. Okay, now make sure you review the part 2 if you're having a hard time recalling. When we measure the line-to-line voltage between line A and line B, we'll see that that is essentially equal to phase A voltage. Similarly, when we measure the line-to-line voltage between line B and line C, it's going to equal phase B voltage. And lastly, when we measure between line C and line A, that's going to equal phase C voltage. Again, this was covered in depthly in part 2. So in this video, we're going to further talk about these voltage quantities on the delta side. Okay, now to begin, let's clarify something. Okay, so the delta has no ground, right? But there is a ground somewhere in our source. Some generator in this source is tied to the ground, and that ground is the reference for this transformer, right? So we're going to assume that it's this particular connection. So we know what the ground is. So we know that this ground is for this source, and this ground is in reference to this particular delta connection. Okay, so now what I'm going to do is I'm going to connect this ground. I'm going to tie that ground to the Y side. Okay, and I'm going to say it's all the same ground, right? Now that I have that established, okay, I have the same reference quantity established. What I'm going to say is that the voltage across line A and this ground point here. So if I measure the voltage across line A and this ground point here, I'm going to call that voltage VAG. Okay, I've drawn the arrows here to indicate that. Now VBG, that's going to be measured across line B and ground. So we're going to add arrows to illustrate that here. Okay, so there's VBG, and now I'm going to make this a little bit better. And lastly, VCG is the voltage across line C and ground. Now the trick to understanding voltage phasors for the delta connection is really rooted in the understanding of VAG versus VAB. Okay, so VAB is the voltage across line A and line B, which is essentially equal to phase A voltage. So we're talking about the difference of understanding phase A voltage versus VA to ground voltage. Okay, and oftentimes this VA to G quantity is also called VAN and is also referred to as this reference quantity. Okay, this reference quantity. And again, Introduction to the Delta Y Transformer Connection, Part 6b. In this part, we're going to continue our discussion on the voltage phasor diagram for delta transformer connection. And by the end of this Part 6 tutorial, not this one, but the Part 6 section, we'll have a greater understanding what this illustration means, how it's drawn, and what it represents. We often find this illustration in transformer nameplates as well as engineering drawings. So we want to have a very strong understanding of this connection. So in part 6a, we set up our voltage phasors and we defined VAG, VBG, and VCG. We also said that there is a difference between VAG versus VAB or V phase A, and that is the key to understanding voltage phasors for the delta connection. Let's just jump right into it, right? So VAB, which is the voltage across line A and line B on the delta side, is equal to the phase A voltage, which is the voltage across winding A. That is also equal to VAG minus VBG, which makes sense, right? VAG is here, which is a voltage across line A and ground, and then VBG is here, which is a voltage across line B and ground. So the voltage across line A and line B is essentially equal to the voltage across line A to ground minus the voltage across line B to ground. Makes sense, right? Okay, so let's evaluate this equation. So I've set something up already. This should look very similar to the examples that we've been doing in our previous tutorials. The first thing that we're going to do is we're going to define our phasor values, right? So I'm going to choose a value for VAG of 2400 volts at 0 degrees. And VBG is again 2400 volts at 240 degrees, and VCG is equal to 2400 volts, 120 degrees. Now, if you haven't caught on already, this is the balanced set of three-phase voltages. And if you're still confused, just click on this link here where you can find a video on balanced power system. Okay, so I'm going to call this phasor VAG because that's how I defined it, right? So VAG is at 0 degrees, and that's the 0 degrees is my reference line, okay? VBG is this phasor here, and VCG is this phasor here. Again, if you're having a hard time understanding this setup, just click on this link and go to that balanced power system video tutorial. Okay, so this right here is an A, B, C phase rotation, okay? Now, we said in our equation that the line-to-line voltage across line A and line B, which essentially equals voltage across our phase A winding for our delta connection, is equal to VAG minus VBG. So here is VAG right here. We're going to perform the head-to-tail method and subtract VAG minus VBG. Okay, so now that we have this visual representation, if we were to relate VAG to VAB, what would we have to do? Well, we would have to shift VAG by 30 degrees. We'd have to shift it by 30 degrees in the counterclockwise direction, okay? And then we would have to multiply it or stretch it, right, by 1.73 or the square root of 3, so it lines up with VAB, okay? So we take VAG, now we have to shift VAG by 30 degrees in the counterclockwise direction, and then we have to multiply it or stretch it by 1.73 so that it overlaps VAB, which means that VAB is equal to the square root of 3 times VAG rotated by 30 degrees, okay? So this equation here, you see that? So why are we doing this, all right? So let's step back and understand exactly what's going on here and why we're doing this. We want to understand the relationship between VAG and VAB, okay? Because that's what's going to help us understand the voltage phasor diagrams for the delta connection. Is that making sense? If it is, comment on below, and if it's not, then tell me how I can improve these videos. Now, if you haven't already, please do go ahead and subscribe by clicking on the link on the bottom right hand corner of the screen. In the next part 6c, we'll go ahead and complete our phasor diagram and show the relationship between these voltages here versus these voltages there. This video was brought to you Introduction to the Delta Y Transformer Connection, Part 6c. In this part, we're going to continue our discussion on the voltage phasor diagram for the delta transformer connection and kind of explain what this means. Okay, so in part 6b, we concluded that VAB, which is this voltage phasor here, that is equal to VAG, which is this voltage phasor here, rotated by 30 degrees and then multiplied by the square root of 3, that's going to equal VAB, okay? So let me write that down here. So VAB, square root of 3 times VAG rotated by 30 degrees. So I'm going to extend that same concept to evaluate VBC and VCA. And that's going to look something like this. So this phasor here is negative VCG, and this phasor here is VBC. So what we're saying is that if we take VBG, right? If we take VBG, we rotate it by 30 degrees in the counterclockwise direction. So we take VBG, we rotate it 30 degrees in the counterclockwise direction. And then if we multiply it by the square root of 3, that's going to equal VBC. And then similarly, we'll do the same thing with VCA. So here's VCA, here's negative VAG. We take VAG, rotate it by 30 degrees in counterclockwise direction, and then multiply it by the square root of 3 to equal VCA, which is this phasor here. So now we have the line to ground voltages as well as the line to line voltages represented in our phasor diagram. Okay, so let's zoom out here and kind of verify this. So remember, VAB is a voltage across this line, these two lines, right? Line A and line B. VBC is a voltage across line B and line C. And then VCA is a voltage across line C and line A. VAG is a voltage across line A and ground. BG is a voltage across line B and ground. And VCG, voltage across line C and ground. Okay, now notice that in part 6a, we said that the line-to-line voltage across line A and line B is equal to phase A voltage. Now if you're having a hard time recalling this, just click on this link here and it'll go to the video exactly where we talked about it. Okay, now let's just label these in our phasor diagram. So remember, VAB is equal to V phase A, VBC is equal to V phase B, and VCA is equal to V phase C on the high voltage side. So here's VAB, we said that that is equal to V phase A, VBC is equal to V phase B, and VCA is equal to V phase C. Now that we've drawn this, we're at a point where we can actually talk about this type of a phasor diagram where we often find in transformer nameplates and as well as engineering drawings, right? But before we get to here, if you haven't already, go ahead and click on the bottom right corner of the screen. There's a subscribe button. Click on that and subscribe to this channel if you haven't already. Okay, so let me just clarify one thing. Okay, so we said that this is VAB or V phase A, right? Which is a voltage across line A to B, which is the same voltage across phase A winding. Okay, now since we've represented this side, right, as the polarity side of our winding, we're going to represent that polarity side by putting a dot here. So we're saying that for this phasor, right, this side is a polarity side. This is for phase A winding, right? And we're doing this just to get a visual understanding. So this right here is a polarity side, and this right here is a polarity side. Alright, so I'm going to now remove some of the things that we don't really need to make this process as simple as possible. Now this is what we do. This is where the magic comes from. Okay, now I'm going to explain this in a little while, but just bear with me and watch what I do to change this phasor diagram to something like this. Okay. Alright, so this is what we have. Okay, now before I explain to you how this works, let's just move it to the left hand side so we have a comparison, right? Left to right comparison. Okay, so first of all, this phasor diagram right here, this is what is referred to as the open form phasor diagram. Okay, and this right here is referred to as the closed form. Now you might ask, well, what's the difference between those two? And that's what we're going to cover. Okay, so now we're at this point where we're going to continue this discussion in part 6D. Now, if you like these videos in Introduction to the Delta Y Transformer Connection, part 6D, this is where we left off in part 6C, okay? Now, in this part, we're going to explain what this means and how this works, right? Now, we said in the last video that this is often referred to as the open form phasor diagram, and this is often referred to as the closed form phasor diagram. Now, the open form versus closed form phasor diagrams have their own advantages, and that's what we're going to talk about in this video. When I was first learning this phasor diagram, the closed form phasor diagram, was very confusing. I never understood it. To be honest, it was only recently that I actually understood what was going on here. The open form was always a lot easier to visually and conceptually understand, but this closed form, it's a work of art. Okay, so the way that it works is that, first of all, it's really helpful to label our phasor windings to get our visual understanding. Now, this phasor here, that's VAG, and it's pointing to this corner of this triangle. So I'm going to call this A. Okay, this is VBG, and it's pointing to this corner here, so I'm going to call this B, and this is VCG, it's pointing at this corner here, so I'm going to call this C. Okay, the number one problem for the closed form phasor diagram is that this triangle, the shape, it makes us mentally think that the triangle represents line to ground A, B, and C voltages of the power system, okay? And we clearly see that it doesn't, right? The triangle actually represents the line-to-line voltage of the delta transformer connection, but that is also equal to the winding voltage, right? But our line-to-ground voltages are actually these inner phasors. That's one of the problems for this closed form, that it makes us think differently, okay, when we first visually inspect it. So the second problem for this closed form phasor diagram is that when we look at this, we think that the origin represents the neutral or the ground. And by inspection, the neutral is equal to the ground. And then the question comes up, well, why is VAN equal to VAG? And then the last thing is number 3, the most confusing thing about this closed form phasor diagram is that why is VAB, right, VBC, and then VCA shown in this particular manner, right? It appears that the voltage drop is, for VAB, for example, this voltage drop should be from B to A, right? Because the arrow is pointing in this direction. So this voltage drop is from B to A, but what we've written down is VAB. Same thing over here. So when we initially inspect it, it appears that this voltage drop, this phasor, should be VAC because we start from A and then we go to C. But in reality, phasor is VCA. And then same thing over here. By inspection, it appears to be VCB, but in reality, it's VBC. So the voltage drop isn't as what we've defined it. That's the third reason why the closed form is so confusing. Although it has its confusion, the content is very true and very correct. We just have to understand what this is telling us. And if we compare that to the open form, everything becomes very, very clear. We know what VAG is, we know what VAB is, and we know what's lagging and what's leading and how much it's lagging and leading and blah, 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 blah. So what's the benefit, I guess? What's the benefit of this form, right? What's the benefit of this closed form phasor diagram? Well, the biggest benefit that this form provides us is that it tells us how the transformer windings for the delta is connected. Let me repeat. This phasor diagram tells us how the transformer windings for the delta connection, how those windings are actually connected. And this is the trick that I'm going to explain. This is what's really neat about this closed form phasor diagram. So let me clean this up. You see this here, this phasor here, we've defined this as this phase A winding, right? Now I'm going to zoom in So we've defined this phasor here as V phase A, right? V phase A. And we said that this side here, the dotted side, is the polarity side of V phase A. Now, look at what the polarity side of V phase A is connected to. It's connected to the non-polarity side of V phase C, right? So this is V phase C. The polarity side of V phase A is connected to the non-polarity side of V phase C. And then look at what the polarity side of V phase C is connected to. That's connected to the non-polarity side of V phase B. And the polarity side of V phase B is connected to the non-polarity side of V phase A. You guys all see that? So let's back up. And then let's compare it to our actual transformer connection. Okay, so what are we actually saying here? We're saying that this phasor here, right? The polarity side of V phase A is connected to the non-polarity side of V phase C. Okay, so this is our phasor here that represents this phasor diagram here. So the polarity side of V phase A, which is this diagram here, polarity side of V phase A, which is this here, that's connected to the non-polarity side of V phase C. Okay, so polarity side of V phase A is connected to non-polarity side of V phase C. The polarity side of V phase C, which is this winding here, that's connected to the non-polarity side of V phase B. So the polarity side of V phase C, which is right here, that's connected to the non-polarity side of V phase B. Okay, and then lastly, the polarity side of V phase B is connected to the non-polarity side of V phase A. So the polarity side of V phase B is connected to the non-polarity side of V phase A. And there you have it. So this closed form phasor diagram, it represents how this transformer is actually physically connected. And that's the most important